Good morning. This is EC 124 second lesson. This morning we'll be looking at EEC semiconductors devices. Basically, we'll look at semiconductor physics before we continue on the part of the electronics. We recall last class that we have classified material as insulators, conductors, and semiconductors. It's important that we do not forget those distinctions between the materials. As I said earlier, we'll be dwelling on semiconductors. So semiconductor materials are elements having conductivity between that of a good conductor and that of an insulator. So remember that with increase in temperature for a metal, conductivity falls. Hence we say they have positive coefficient of resistance. But semiconductor materials have negative coefficient of resistance, meaning when you increase the temperature, some electron in the valence band will gain sufficient energy and move to the conduction band, so they conduct more at higher temperature. So semiconductor materials having conductivity between those of good conductors and those of insulators. So these materials are either single crystal semiconductors, that is, you have just an element in a crystal. For example, you have germanium and you have silicon. Or you could have it in compound, where you have more than an element forming a compound. Remember the definition of a compound: you have more than one element chemically combined together. So here you have gallium and arsenic coming together to form gallium arsenide, and you have cadmium and sulfur too forming cadmium sulfide, and you have gallium and nitrogen forming gallium nitride, and gallium arsenic and phosphorus forming gallium arsenide phosphide. So a semiconductor material is either a single crystal semiconductor or a compound semiconductor. So the most frequently used semiconductors in electronic devices are germanium, silicon, and gallium arsenide. Don't forget, gallium arsenide is a compound semiconductor, while germanium and silicon are single crystal substance. So silicon and germanium have 14 and 32 orbiting electrons respectively. So the number of electrons in silicon is 14. That of germanium is 32. So if we use Bohr atomic model, each of them has 4 valence electrons. Gallium arsenide is a compound too, so there is a covalent bond between gallium and arsenic. So we will not be dwelling too much on that. So we may actually be using silicon for ease of our understanding, but we see that this germanium and silicon has 4 valence electrons, and elements that has 4 valence electrons are termed tetravalent, meaning tetra 4, valence from the word valency. So silicon has 4 valence electrons, so it's tetravalent, meaning for the structure to be stable, there is need for each of these silicon atom in the crystal to have 4 more electrons for it to be stable. However, this stability can only be achieved by sharing of electron. So each silicon atom now has 4 orbiting valence electrons. Remember this is 284, so we'll not be looking at the first 2 inner shells, so we'll concentrate more on the outer shell, which determines chemical properties of any element, valence electron. Now you see this 4, 1, 2, 3, 4 that need 4 extra. So the elements in the center now, let's pick any silicon atom. We have 1, 2, 3, 4. So it's going to bond with one from the neighboring silicon atom, one from here, one from here, and one from here. So this now has 8 valence electron. This one too do the similar thing. So meaning for it to be stable, it means 4 outermost, 4 electrons to combine. So by the time this combination takes place, since it's a sharing of electron, so it is a covalent bond and gives it more stability. Now, for semiconductors are either intrinsic or extrinsic semiconductor. Intrinsic and extrinsic. An intrinsic semiconductor is a semiconductor material that has been carefully refined to reduce the amount of impurity to a very low level, essentially as pure as can be made available through modern technology. So the idea here is that not that it will be totally pure from impurity. There may still be some trace of impurity, but we will try as much as possible to refine it carefully to a very low insignificant level of impurity as current technology permits. But when we say extrinsic, extrinsic can only be made from a pure semiconductor, which is intrinsic semiconductor. So when you have an intrinsic semiconductor, one that has been carefully refined, and this one is now subjected to doping, that's when you now have an extrinsic semiconductor. So we need to understand what the term doping means. Doping is a process of adding calculated amount of impurity. This is usually in minute quantity, very small quantity, 1 part per million in some case, of impurity to an intrinsic semiconductor material. So when you add a doping agent to a semiconductor material, an intrinsic semiconductor, then you have add what? An extrinsic semiconductor, and this is to improve its electrical conductivity. So when we dope a semiconductor material, its conductivity increases. In an intrinsic state, the semiconductor material conduction is due to electrons and holes, and these electrons are the electrons that have gained sufficient energy to move to the conduction band. Remember the energy bands: valency band, the energy gap, and conduction band. So for an electron to conduct, it has to be in the conduction band. So it is few ones that have gained some thermal or light energy to move to the conduction band and then conduct. And by the time this one leaves their valence band, there will be some holes that are left behind. So the holes are positive electrons and negative. So conduction in semiconductor is due to holes and electrons. Holes being positive, electrons being negative. So by the time we dope, we try to improve this conductivity. So we explain doping as we go on. Now, extrinsic semiconductor proper now. A p-type semiconductor is formed by adding a trivalent atom. That's an atom with 3 valence electrons. Now, you look at boron with atomic number 5. Boron has a configuration of 2, 3, meaning the valence electron is 3, and so on. So you look at aluminium too. Aluminium has 13, so 2, 8, 3. The 3 there is the valence electron. So to make a p-type semiconductor, we add a trivalent impurity, which is trivalent atom. So example of trivalent atoms are aluminium, boron, gallium, and indium. So diverse impurity with trivalent atoms are called acceptor atoms. They are called acceptor atoms because they create holes that easily accept electron. Now let's look at n-type semiconductor. For us to make n-type semiconductor, we add pentavalent impurity atom, e.g. antimony, phosphorus, and arsenic. The one in first 20 element that we easily remember is phosphorus. We know phosphorus is atomic number 50. By configuration, it will be 285, meaning it has 5 valence electron. So the 5 valence electron, if you now introduce it into a kind of bond that you introduce it. You remember this silicon can only donate one. This boron now, let's say, is at the center. Okay, let's use antimony, which is a 5-valent atom, pentavalent atom. So antimony at the center will donate one to this silicon, one to this, one to this, one to this, but there is still one in electron. So this electron that is now present will now make it to be a donor impurity, meaning this can easily be donated. That's why we call it donor impurity. So this is an n-type material. But if you look at boron, for instance, boron has 3. It has donated one to this, one to this, and one to this. This, the fourth electron, fourth silicon atom, will also need its own one, but this will create a hole. This hole will now make an acceptor impurity. But here you have electron from the fifth electron from antimony makes it what? Donor impurity. Now we look at this p-type closely more. So aluminum at the center. Aluminum can only donate 1, 2, 3. The fourth here will now be a hole. There is no electron. Deliberately it is made a circle without a black dot so that we know it's a hole. But these ones are electron. So by the time we a crystal that needs 4 electron, outermost electron in each case, tetravalent, you now introduce a trivalent atom. That means there will be a deficiency of 1 electron that will constitute an hole. So that's why it's called an acceptor impurity. So to make a p-type semiconductor, extrinsic semiconductor, we use a trivalent atom. But to use n-type semiconductor, we use what? Pentavalent atom. Now let's talk about majority and minority carrier. Like I said earlier, in intrinsic state, number of free electrons is due to free electrons in the valence band that have acquired sufficient energy from thermal, that is heat or light sources, to break the covalent bond of few impurities that could not be removed. We talk about intrinsic semiconductor, we say it is carefully refined to a very low level as modern technology permits. So there could still be some impurity present that were not removed. So the electrons in this case, could cause conduction, or those electrons that have gained sufficient energy to leave the valence band and move towards conduction band. So when electrons gain energy and move to conduction band, they leave holes. The vacancy left behind in the covalent structure represents the limited supply of holes. So in the intrinsic state, there's limited amount of holes and electrons. But by the time, regardless of whether we excite it or not, though as we excite it, there will be more and more, but the conductivity will not be as good as that of extrinsic state. So when it's now in an extrinsic state, either in n-type or as p-type, the number of holes has not changed similarly for n-type, because there are more electrons due to each of the donor impurity. So the number of electrons has outweighed that of the number of holes. It will similarly outweigh the number of electrons. So that means there will be more electrons than holes in n-type semiconductor, much more. So electrons are the majority carrier and holes are the minority carrier in n-type semiconductor. Also in p-type material, the number of electrons has not changed significantly from the intrinsic level, because there are more holes now, and the number of holes now outweighs the number of electrons. Hence, holes are the majority carrier. and the electrons minority carrier. So take note that in n-type material, electrons are the majority carrier and holes the minority carrier, and in p-type material, holes are the majority carrier and electrons the minority carrier. Take note, though holes are positive, electrons are negative, but you remember that the element introduced here still has its proton and neutrons intact. Protons are positively charged, electrons are negatively charged. So the whole substance is still electrically neutral. Not because you have excess electron in the electron cloud now makes this compound negative or positive. No, because the electrons and the holes, electrons and protons in the nucleus of the atoms remains the same. So now let's look at this image for a p-type material. You notice that in the proton and in the nucleus of the atom there are uh, protons and neutrons. Protons are positively charged, neutrons are negatively charged. So because of the presence of holes here, so electrons can easily move to p-type material. So we say these ions are acceptor impurity because there is still but the holes here you see are not encircled, so they are the majority carrier. The same goes for n-type material. These are donor ions. They are now ionized because electrons have left the base atom, and you know, for an electrically neutral atom, number of protons and electrons are the same. But now the electrons have left the parent atom. So since there is now more protons than electrons, then the donor ion are positively charged. Mind you, the whole of the substance is negatively charged. Now having known how to form p-type and n-type material, we form the first electronic component called diode. A diode is formed by simply bringing a p-type semiconductor in contact with an n-type semiconductor. A p-type semiconductor, silicon in this case, has silicon in the case of n-type too, meaning these are what is responsible for conduction here are holes, majority carrier, and the minority carrier electron. Here majority carrier electrons and minority carrier holes. So this terminal with p part is termed anode. The terminal with the n-type semiconductor is the cathode. So electronic symbol is basically like this. You have a triangle like this, like a gate. So this part is the anode and this part is the cathode. So anode and cathode. So we study this substance, this device more. These are first semiconductor device, which we term that we study it much more and more detail. So we'll understand later that diode has performed some function. Basically, we say diode, you could use it as rectifier, you use it in modulation, in demodulation, and so on and so forth. You can use it in protection, so on. So we'll dwell more on this as a whole. So, but we should know the circuit symbol for this, and we should know the terminal, which is the anode, and the terminal, which is the cathode. So next class we will dwell more on this particular material that we call